Welcome to section 4.1, Extreme Values of Functions. In the first section of chapter 4, you'll be learning how to use basic calculus and the use of derivatives to find the extreme values of a function. Using these extremes will allow us to solve other problems such as finding the maximum and minimum values or height using a given equation. By the end of this section, we will also be defining and distinguishing the difference between absolute or global extremes and local or relative extreme values. Understanding and being able to recognize what these different extremes of a function are will help us to solve more difficult problems down the line. So let's jump right in and learn the ins and outs, or ups and downs rather, of section 4.1. We will first begin by defining an absolute or global extreme of a function. The word absolute simply implies that in a given equation or on a particular interval, there's only one maximum or one minimum value, as shown in these two equations, y equals x squared and y equals x. The equation y equals x squared has only one extreme value on any interval, as you can see from the bottom of the curve. Therefore, this value would be called an absolute or global minimum at point 0, 0. The same applies to the equation y equals x in a slightly different way. The function y equals x on its own has no extreme values, but when given restraints such as the interval -2 to 2, the equation would then have both an extreme maximum value at 2, 2 and an extreme minimum value at -2, -2. A more clear example of an absolute extreme value would be a function that looks like this. This graph has more than one maximum and minimum value. The extreme that is the greatest overall is the absolute. That leads us right into finding the local or relative extreme values of an equation. The function that we just covered with the multiple extremes is a perfect example for local extremes as well. The points that we found before and labeled the absolute extreme values are the absolute highest and lowest values, as we already covered. The remaining maximum and minimum extremes are what we call local or relative extreme values. Not all of the extreme values of a function have been covered and labeled, so there will be no confusion. Now that we're able to distinguish local from absolute values, you can use the local extreme value theorem to determine at what point in the function the derivative is equal to 0. The local extreme value theorem states that if a function f has a local maximum value or a local minimum value at an interior point C of its domain, and if f prime exists at C, then f prime of C equals 0. An example of this theorem would be to use a function f of x equals the cosine of x on the interval 0 to 2 pi. We can see that this function has an extreme value at x equals pi. Because of the local extreme value theorem, we know that the derivative of the function f of x equals the cosine of x at x equals pi is 0. Another theorem that we learned from section 4.1 is the extreme value theorem, an extremely important theorem which we use to find the extreme values of a function when we are given the function. The extreme value theorem states that if f is continuous on a closed interval a, b, then f has both a maximum and a minimum value, and a minimum value on the interval. For example, if you're given the function y equals 3x to the 4th minus 4x to the 3rd on the interval -1, 2, you can use the extreme value theorem like this. The first step is to take the derivative of the function, y equals 3x to the 4th minus 4x to the 3rd. We know that the derivative is 12x to the 3rd minus 12x squared. Then you will want to find the zeros of your derivative, or set your derivative equal to 0. In doing so, you find that your x's are 0 and 1. Now that you have the zeros of the derivative of your function, you can plug them back into your original equation, along with your domains, or your interval, to find the y values of your extreme values. The zeros that you found give you the x values for your extremes. F of 0 equals 0, f of 1 equals -1, f of -1 equals 7, and f of 2 equals 16. By looking at your graph, you know that your absolute maximum is y equals 16, and your absolute minimum is y equals -1. Now, remembering the steps again for using the extreme value theorem, first, look at the graph, using a calculator if necessary. 2. Finding the critical values, the zeros and the undefined values. 3. substituting values into the original function f of x, and 4, substituting in the endpoints into the original function f of x. Try solving this homework problem. Given the function f of x equals x to the 2/5, use analytical methods to find the extreme values of the function on the interval -3, 1. Done? Okay. First we are going to look at the graph of our function to get an idea of what it should end up being. The next step is to take the derivative of our function, f of x equals x to the 2/5. This comes out to be 2 over 5 times x to the 3/5. The next step in using the extreme value theorem is to set the newly found derivative equal to 0. This will give you the 0 of the function, which happens to be located at x equals 0. Finally, we are going to plug the 0 back into the original equation, along with the restraints, or endpoints given in the problem. F of 0 equals 0, f of -3 equals 3 to the 2/5, f of 1 equals 1. By looking back at our graph, we can see that there is an absolute max at -3, 3 to the 2/5, and an absolute minimum at 0, 0. In addition to finding extremes, it's also important to be able to understand and be able to find a critical point in a function. A critical point is the interior of the domain of f of x at which f prime of x equals 0, or f prime of x does not exist. An example of a critical point would be found in the function f of x equals the absolute value of x. The graph of the function f of x equals the absolute value of x looks like this. Because we know that the derivative cannot be taken at a corner in an equation, we know that the derivative of f of x at 0 does not exist. Even though this function is not differentiable at that point 0, 0, however, that point is still considered an extreme value and an absolute minimum of the function. Now that you understand both critical points and extreme values, I'll have you try another homework problem. Suppose you were given the piecewise function, y equals -x squared minus 2x plus 4, x is less than or equal to 1, and y equals -x squared plus 6x minus 4, where x is greater than 1. Identify the critical points and determine the local extreme values. The first step in solving this problem is to separate the two equations, y equals -x squared minus 2x plus 4, and y equals -x squared plus 6x minus 4. The next step will be to take the derivatives of both of the functions and set them equal to 0. This will get you your zeros, which are x equals -1 and x equals 3. These zeros that we found are critical points of the function, along with the domain of x equals 0. Then, just as we did before, we're going to plug the zeros and the restraints back into the original function. That will give us f of -1 equals 5, f of 1 equals 1, f of 3 equals 5. And by looking at our graph, we can see that -1, 5 is a max, along with 3, 5. And 1, 1 is our minimum.